Yeah. All right. Again, welcome everybody. We had 35 on Tuesday. We have 28 now. People are moving around between courses, and that's totally fine. What I'm going to do today is finish my storytelling and hopefully motivate you for the kinds of things you can start thinking about after you've taken this course. And then we're going to dive into a little bit of math. Oops, hello. But first, a couple of announcements. There's a problem set due next Tuesday. It is posted, the document itself is posted on my course webpage, but it is due on Canvas. I apologize for the confusing nature of this. We talked about this. You submit it on Canvas. I'll grade it on Canvas. It's due, I don't know, say by 5 o'clock. I won't start grading probably until Wednesday morning, but don't stay up all night. It's not worth it. I posted the MP4 file for Tuesday's lecture under a module on Canvas that I learned how to use thanks to one of your classmates helping me. I will also put PDFs of my slides there. But as you've noticed, I don't put the entire content of the course on PowerPoint slides. And that is not just because I'm a dinosaur, although I am. I have a reason for this. Because PowerPoint puts people into a passive mode of absorption of information, and I want an active mode of absorption of information in this class. There is information in the progression when I make a drawing. And it also slows me down to the point where I don't bludgeon you with information and we all say, oh, well, they can go look at the slides later. There's also information, or there's learning in the fact that it goes in your head, it goes down your arm, it goes out your pen into your notebook, and you're digesting it in your own way in real time. So all of these are reasons why I use written materials. And when we get to the classroom, you'll see, chalk and colored chalk on a blackboard for exactly that reason. So what that means is that the PDFs of my slides are not a complete capture of what's going on in this class. And that's part of why, hey, don't scratch the sofa. Excuse me. Part of why I need to move the newspaper off his bed. Hang on. Cats. Anyway, any issues on the MOOC, please just yell.
I wanted to ask logistics for the first problem set, basically with the MOOC. Essentially, it says that you should watch the videos corresponding to the days, and I was wondering if the days were after the problem set or before the problem set is due.
Okay. The MOOC course is way lower level than this course. So if you're getting the material in the lecture, it doesn't matter when you get the timing of the videos. So what I would suggest is if you sit down with the problem set and something's not making sense, go back to, well, first your notes, but then go to the videos. Does that help?
Yes, that does.
Okay. Any other questions on that?
Yeah. So on the MOOC, it has like the videos, the quizzes, and the homeworks. I know the quizzes are whenever you feel like it. Are the homeworks like graded or anything?
Good question. Those homeworks, don't bother with the homeworks. You're doing harder homeworks in the class, so don't bother with the homeworks on the MOOC. I should have said that. I apologize. Thank you. You can look at them, but they'll be you're doing harder ones in the class.
Also in the supplementary materials section, are those required, like readings and videos and stuff?
No, those are just for your use. That's all.
Okay, cool.
Yeah. Okay, and I'm glad you guys, you folks, actually, ladies, at that point, just say something if you're trying to. I can't track. I've got so much technology going on around me and the cat, and it's impossible to also track the Zoom chat. So if you guys want to use the Zoom chat among yourselves, that's fine. Like, what did she say? Oh, I think she said that's perfect. But if you need me to be attending to what you're thinking about, you need to just unmute and say something. Okay. All right. So I ended the last lecture with some storytelling and storytelling about chaos. Not only the rich and interesting history that I talked about on Tuesday, it has a rich and interesting set of applications. Beginning with fluid flows, this is why we use the eddy as an example. Weather is also fluid and heat flow. And in fact, weather is nonlinear and chaotic. And this is part of why it's actually ties back to a point that I made on Tuesday about, hey, this system is deterministic, but it's effectively unpredictable. And isn't that weird? Because if the system's deterministic, the current state should allow us to completely predict for all time what's going to happen. But the problem is we don't have perfect knowledge about the state. We don't have perfect knowledge about the dynamics. And in the presence of imperfect knowledge, sensitive dependence on initial conditions can take the little imperfections in our knowledge and amplify it into huge effects that trash our predictions. This is why weather.com only goes out 10 days. I have a colleague in the civil engineering department named John Cromaldi who has figured out that marine invertebrates employ chaotic mixing in order to spawn. So the boy clam and the girl clam spit out eggs and sperm, and they do this in such a way and they manipulate their shells so that there's chaotic mixing that mixes the eggs and sperm together and make little clams, which is pretty cool. There's a lot of interesting heat and fluid flow in combustion chambers, including the cylinder head of your car. And perhaps the butterfly effect could be turned to advantage in that situation. And I've done a bit of work on that I'll come back to at the end of the semester. Oscillators. This goes back to Huygens and his clocks and pendulums all synchronizing on the wall. It's not just the case that, boring old pendulums they're nonlinear. If you force them the right way, they can be chaotic. Here's a driven nonlinear oscillator right in here. Your heart is a nonlinear oscillator, and it goes, P, Q, R, S, T, and it's largely periodic. The beat-to-beat interval is not not perfectly periodic, but the waveform kind of looks the same most of the time, until you go into ventricular fibrillation, at which point your EKG looks very chaotic and it's pretty much immediately fatal. So hearts can be chaotic. Brains are normally chaotic. If you take a rabbit and you hook an EEG to the olfactory bulb area of its skull, and you give it a smell that it knows, the EEG looks quite periodic. But if you give the rabbit a smell it doesn't know, that EEG starts looking chaotic. We humans, some of us, not all of us, have observed this effect. There are certain recreational drugs that make your brain transition from its normal chaotic, healthy state to a more periodic state. So don't try this at home, right? There's a ton of interesting work with fireflies, not just our textbook author, but also Orit Peleg in our department has done some really cool work with not just that these things can flash, but that they couple, just like Huygens clocks on the wall, and they couple and they all end up flashing at the same time. And I'm cherry picking again, like I was on Tuesdays. There's lots and lots of other examples in all sorts of branches of science and engineering, including things off the Earth. So in the solar system, in the universe, all sorts of interesting nonlinear and chaotic dynamics come up. Now, you probably remember from physics that if you have two bodies and they're pulling on each other, that's that GMM over R squared kind of pull. There's two bodies, only a small set of things can happen. Conic sections, ellipses, parabolas, hyperbolas. That's all that two bodies in interaction can do. That goes back to Kepler and Newton. But if you add a third body to the mix, that all goes out the window and the system can be chaotic. And that word can, Poincaré, who we mentioned on Tuesday, he did some work on this and he made that word, he did a proof of when that word can becomes is. So that was one of his contributions. And that's not easy. To prove that a system is chaotic is not easy. Lots of other examples in the solar system and the universe around us that we'll get back to. Proteins, when proteins fold up, there's some evidence that after they fold, they kind of sit there and breathe a little bit, and maybe that dynamics is chaotic. And there's a ton of chaos in population biology, some of which we'll get back to later today. And again, cherry picking the computer that I'm using to give this lecture, computers are nonlinear and high dimensional, right? High dimensional, lots of transistors, each of which has a state, it's 0 or 1, or it's a certain voltage. And they're certainly transistors or switches, so they're nonlinear. So it shouldn't be surprising that it could be the case that computers are chaotic. Turns out they are. I'll come back to that as well. Not in the sense of the results that they produce are chaotic, although sometimes when we're learning to program, we think that's true. More that the way they use their memory and their processors as they're producing those results is chaotic. And that's quite interesting. It was fairly upsetting to the computer systems community, and they don't like me, but that's okay. All right, a little bit of vocabulary. In all of my examples, most of my examples at least, I chose examples where there were different kinds of behavior. I chose an example where the heart could be periodic or it could be chaotic, and the brain could be periodic or it could be chaotic. So the same system is acting differently depending on the conditions around it. So there's some sort of knob that the biology is turning, or the chemistry is turning, or the physics is turning, that causes the system to behave differently. It rains up in Netherlands, so the rock that's making that eddy in the creek, the eddy changes shape. These are all called bifurcations. This is an important term, bifurcation. The word as written looks like it should mean that something splits in half. We use it in my field to describe an event that causes a qualitative change in the behavior, the long-term behavior of the system, what's called the asymptotic behavior or the attractor. We'll come back to that. The asymptotic behavior of the system, after the transient dies out, what the system does, that's called the attractor, and a bifurcation changes that. And bifurcations happen under the influence of parameters like blood chemicals, like the smell, like how much it's rained in Netherlands. All those are physical, biological, chemical, mathematical knobs that reach into the equations and change stuff, reach into the system and change stuff. So bifurcations happen under the influence of parameters in dynamical systems. Just trying to get you used to some of the language. Okay, so I've used some of this terminology. I've snuck some of it in, and I wanted to get back to this a little bit. Now I'm trying a different configuration with the document camera today. I've got it on the right-hand side, but that means that every darn time I switch, I have to hit a button to make it do that. So my apologies. Oh, and this is a slide, or hello, hang on a second. This slide right here, or this piece of paper, I was going too quickly and I had a mega there. It should be a theta. That's why this has a great big red X through it. So these are the kinds of things that, please, if I do this, or if I lose a minus sign, or if I do something like that, please yell in class or raise your hand when we get back in person. That should be a theta. Thanks to Corey for catching that. Okay, back here. Hello. Darn it. All right, so trajectories and parameters and bifurcations and attractors. I just talked about bifurcations and parameters, and bifurcations happen in attractors. Attractor is a very important word in this field, and we'll do a bunch on it today. It means, again, the long-term asymptotic behavior of the system after the transient dies out. Trajectory. So a trajectory is typically applied to, it's a name for a thing in state space. It is the path through state space that the system will follow from a given initial condition if you let it go. Okay, so a trajectory is like we were drawing in the state space of the damped pendulum. Actually, why don't I just draw some stuff? Okay. Do this, flip the camera. I don't know why it does that. I will fix this. Okay, so in the damped pendulum, that's the pendulum with some friction in it. We did some work on this the other day. We can plot it in the time domain. We can plot theta of t as a function of time. And I don't know, maybe it does something like that. And it's got some friction, so it's dying out like so. It's damped. And we can plot the angular velocity, omega, as a function of t. And I've got to get this right. Let's see, there is where the max is maximum. This is 0, that's maximum negative, something like that. Oops, I should make it bigger so that it can get smaller like that. Okay. This is the time domain. We use the time domain when we want the details of what's going on with time. But we can also use the state space. That is that incredibly powerful space. It's a representation that whose axes are the state variables of the system, which I defined the other day. And in this state, with this representation, which we use when we want to understand the long-term asymptotic behavior of the system, there's some initial condition. Let's see, I used omega equals 0, theta equals something. So I used this point right here. And if you combine this on the x-axis and this on the y-axis, what you get is an inward spiral. Like that. And what's going on here is the pendulum, I don't know if this is going to work, is swinging down. It's not going to work. So the pendulum is swinging down like this, and eventually ends up pointing straight down, and it stays there. So that is this point in the state space. Theta equals 0, omega equals 0. That's a point in the state space that is an attractor. That's an attractor, okay? And it's an attractor because, and I think I will switch cameras so that I can mess around with my pendulum a bit. Hopefully this will work. And I should put this on because the black background is not good. Hang on. There we go. Pendulum facing you. There we go. So what I've just drawn is some graphs on a piece of paper that are describing this. The top pair of graphs were describing it in the time domain. The bottom one was describing it in the state space. And I could start the pendulum here and it would end up there. I could start the pendulum here and it would take a little more time and it would end up there. The there is a point in the state space. It's a single value of theta and a single value of omega. So it's a point in the state space. It's called a fixed point if the system doesn't move when you put it there. That's a technical term, a fixed point. Okay. This is a fixed point. And by the way, this is also a fixed point. Definition. I put the system there, it stays there. The system derivative is 0. Nothing moves. The system doesn't move if I put it there. However, that fixed point is fundamentally different from that one in that it reacts differently to perturbations. We call this a stable fixed point, and we call this an unstable fixed point. Okay, so they're both fixed points. Switch, flip. God, that's annoying. Anyway, so a fixed point means system doesn't move. From that state. Stability has, and that really has something to do with the derivative, the system derivative. I'll go back to that. Stability has to do with what happens to perturbations. Does a perturbation, which I think I can spell, does it grow or does it shrink? And if it grows, that's called an unstable fixed point. If it shrinks, it's called a stable fixed point. Or it also could be called an attracting, can't spell. Attracting, and this could be called a repelling. My writing gets better when I'm doing it in chalk on the board. So a fixed point is simply about what happens at that point. Stability is you need to know something about what happens near that point. So these are both fixed points. This and this are both fixed points, but one is an attractor and one is a repeller. It's kind of intuitive. Oops. Did that, we did that. Okay. Going back to, find my plots. Going back to this plot, I will get this camera working at some point. Going back to these plots, let's do a thought question, thought experiment. I need to make this bigger so I can see it. Hang on. There we go. What would happen to these plots if there were no friction in the pendulum? We know what would happen to the pendulum. It would just swing forever. And what that would translate to is how the plots would change, this thing would just be a sine wave of exactly the same height all the way out to infinity. This thing would turn into a closed curve. So if there were no friction, I'll do it in blue, there would be a sine wave that just went forever. It wouldn't die out. And this thing would just go around like that for forever. Now, here's the interesting question, and this is a little bit of a technicality. Are there any attractors in that situation? Technically, no, okay? And the reason for that is that business of attractors attracting things. An attractor sits there, and if there's any nearby trajectory, it vacuums it up. It attracts it. So that attraction is necessary. An attraction has to kind of suck things in. But if you just have a device that's going to wiggle like this forever, and if I make a slightly smaller perturbation, it's going to wiggle there forever, and I make a slightly smaller perturbation, it's never going to go into the attractor. So that thing is not an attractor. But there are fixed points. If there's no friction, this fixed point's still there. This fixed point's still there. It's just that it's what happens around them that's different. So there are certainly fixed points in that situation. And it gets even a little bit more complicated, because if you are keeping track at this joint of the pendulum of the full Monty of the angle, that is, it's going 2 pi, 4 pi, 6 pi, 8 pi. If you are keeping track in that way, there are an infinite number of fixed points. Because there's one, there's one, there's one, okay? You see the point? So there's an infinite number of these things that are all 2 pi apart, and half of them are stable and half of them are unstable. And this matters if you are keeping track of theta in a really complete way. Some of you might be old enough to remember telephones that had cords that went to the wall, in which case, if you didn't keep track of how many times things had spun, the cords got all like this. So if you want to have, if you are keeping track of theta in gory detail like that, but you want to kind of project it down to how we look at the pendulum, you're actually doing a modulo operation, either mod plus or minus pi or mod 0 to 2 pi. Okay, so there's 4 kinds of attractors in dynamical systems. The fixed point, which we have now beaten somewhat to death. There's a fixed point. And on my slide is a picture of what the trajectory from some initial condition. Here's the initial condition. The initial condition, the trajectory is going through this transient, going down to this attractor. It happens to be an attracting fixed point. Okay, that's one kind of attractor. There are also other kinds of attractors that are quite interesting. For example, a limit cycle. A limit cycle, I have one. Hang on, I have one right here. Okay. This is the power cord for my computer. Okay. And on this side of the power cord, this is the side going to the computer, there's a DC voltage, 12 volts, fixed volt. This is a fixed point. But over here, there we go. This is the cord coming from the wall. Living in here is not a fixed voltage. It is a sine wave that is 110 volts in amplitude and 60 hertz in frequency. So the power system that feeds the outlets in my room is a dynamical system that is designed to have a limit cycle attractor, limit cycle also known as periodic orbit, that has that form. It has 110 volt amplitude and it goes around 1/60th of a second. Now, isn't it an attractor? Well, we can test that by plugging in, say, a refrigerator and seeing if the attractor changes. There might be a little perturbation. You probably won't see it, but the attractor, the wall voltage won't change. Now, if everybody in Los Angeles turns on their air conditioners at the same time, that may not still be true. Indeed, that might create a bifurcation to a very different kind of attractor, which is a fixed point at 0. That's called a blackout. Okay. So limit cycles or periodic orbits can take on different periods. So if I take my pendulum and I wiggle it at a certain frequency, I can get it to go boom, 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 boom. If I wiggle a little faster, I can get it to go boom, 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 foom, foom. So those are both periodic things, but they have a different period. Let me draw some pictures in state space. Camera. So one of those, the foom, foom, foom one, might look like this. Kind of like the wall voltage in the outlet right here. But the double thing might look like this. Okay, and you can get arbitrarily more complicated limit cycles. So these are all limit cycles, also known as periodic orbits. Of different periods. Now, the definition of period is a little bit wiggly, and some of you may have thought of that. How do you think about period? Well, it depends how you slice, and we'll come back to that. So those are limit cycles.
Why isn't a frictionless pendulum a limit cycle?
It is a limit cycle, but it's not an attracting limit cycle. Good question. Yes. So I'm now talking, I'm projecting down to talking about the 4 different kinds of attractors. So it is a periodic orbit. It is a limit cycle. It's not an attracting limit cycle. So what I'm doing now is attractor types. That's all. But yes, important distinction. Thank you. Okay. So now I can actually, given that I've got this picture on my desk, I can say a little bit more about bifurcations. Because imagine that I change some physical knob and this thing gets a little smaller, or it develops some kind of dents in it, something like that. So these changes here, from that to that, or from that to that, or from that to that, those are not bifurcations because they're just geometric changes. But from here to here, from here to here, that is a qualitative change. This thing used to have 1 loop, now it has 2. That is a change in the topology. And so that is a bifurcation. So a topological change in the attractor, and we will get back to this a fair bit later on. So if your attractor was a fixed point and it turns into a limit cycle, that goes from something that's dimension 0 to dimension 1. That's pretty clearly a change in the topology for those of you who know a bit about topology. If you have something that, well, we'll get much more into this later on. Okay, then there's another type of attractor. It's kind of fun. A way to think about this one is imagine a top. So that, you know, one of those things that you spin with your hand and it spins, but it also precesses as it's spinning. It does this. Now imagine taking a laser pointer and taping it to the axis of the top and watching what it does on the ceiling. What you would see is something like this. Okay. And if the frequency with which, call the pencil, if this frequency, the frequency with which it goes around this way, the precession frequency, no, the rotation frequency and the precession frequency are incommensurate, then it will never be the case that as I draw this around, some round, it's never going to close. It will not close if these are incommensurate. And that's what's called a quasi-periodic orbit. It's not quite periodic, but it's not very much more complicated. Okay. And we're not going to talk about these too much because we're going to spend most of our time talking about these very interesting creatures. These are chaotic attractors, or as Jim York calls them, strange attractors, because they were pretty strange when they were first found. And they have a variety of really interesting properties that we'll spend a lot of time on, including the fact that they are often fractal, not always, but often. That is, in this particular case, if you slice the thing across that red line, excuse me, you'll get a Cantor set, an infinitely self-similar set of points. They are covered densely by the trajectories that relax to them. That little purple ball, it is the case that no matter how small I make that ball, any trajectory from anywhere in the what's called basin of attraction of that attractor, which I will define. Let's hit my gray button here, see if that works. will eventually get into that little purple ball, no matter how small I make the purple ball. If any of you have taken control theory, you can probably see that that's going to be useful. It is also the case that if you take a point on a chaotic attractor and then you take another point very, very close by, and you track the distance between them, the distance between those 2 points, it grows exponentially fast with time. That is the technical definition of sensitive dependence on initial conditions. And there's an obvious issue there with, well, wait a minute, this thing is bounded. How can anything possibly grow infinitely fast? And we will get back to that. Get this cord off my desk. Oh, well. I'll get this figured out just as soon as we go to the classroom. Okay, where am I? Better to switch that way. Okay, so technically speaking, an attractor is what's left after the transient dies out, which is, I know it's a circular definition. We can make it more formal later on, but it is just what it sounds like. You have the system is doing something, and then over time it relaxes to some subset of the state space and just repeats, or may not repeat, it just continues to occupy that subset of the state space. There is a bit of a technicality in regard to those italicized words. For the mathematicians in the room, a trajectory from a dynamical system never actually gets to the attractor. It just gets infinitely close. In practical terms, we don't worry about that too much, but that is an important technicality. And by the way, just a meta point, we have people in this class from computer science, applied math, aerospace, ATOC, and that means that I'm going to be kind of saying, for people who know X, blah, 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 blah. For people who know X, blah, 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 blah. That doesn't mean that everybody is responsible for all of those things. It's mostly to make contact with people who have a little bit more background in one particular subfield. So don't panic about all the little tangents, but grab them and enjoy them if they're yours. Okay. Okay. I used this word before. I want to define it. I've used all the words that are in plain font and defined them. I have not defined basin of attraction. Basin of attraction is basically just what it sounds like. And what causes this issue to arise? Nonlinear dynamical systems can have different regimes in different parts of the state space. In this part of the state space, there could be a chaotic attractor. And over here, there could be a fixed point attractor. And each of those attractors has its own region within which it attracts things. An easy way to think about this is to think about the continental divide in the United States. Most of you, I think, are aware of this. For those of you who are not, any raindrop that falls to the east of the continental divide eventually gets down to the Atlantic Ocean. And any raindrop that goes to the west of the continental divide eventually ends up in the Pacific. So you can think about this. This is the metaphor. And weird stuff happens in Wyoming. This is right on Route 80, and you can drive through what's called the Great Divide Basin, which is kind of cool. So there's really three attractors in this picture: the Atlantic, the Pacific, and whatever the heck lives in the middle of that. And you can think about a raindrop put down here in Nebraska as an initial, oh, lost my cursor, initial condition in Nebraska, and that raindrop will go down the Mississippi and eventually out to the Atlantic. So that's a trajectory from an initial condition starting in the basin of attraction of the attractor that is the Atlantic Ocean. Same thing with the Pacific. A raindrop here in Idaho will run down somehow to the Pacific. That's the trajectory from the initial condition of the dynamical system in Idaho, and that trajectory ends up in the attractor of the Pacific. If you are a raindrop that you fall right smack on the divide, you don't go either place. We'll come back to that. If you back up a little bit, the situation is actually way more complicated and quite beautiful. The Great Divide Basin is not the only weird thing that happens, but this is not about chaos. This is just about pretty pictures. My internet connection is unstable. Oh, well, hopefully that'll go away. This picture also brings me to another interesting point, which relates to the question that the gentleman asked. Something has to eat up the energy. Like in my pendulum, if the pendulum didn't have any friction, there wouldn't be an attractor. It would just rock there forever. But because there's friction, the friction kind of munches up the initial energy of the trajectory, leaving on the way down to the attractor. So something has to change the energy in the system in order to cause the asymptotic behavior to be different than how it starts out. And one way to think about this is to imagine dropping raindrops all over every state to the east of the divide. So you're dropping a bazillion raindrops, one every single county in the United States, and you're tracking them and you're letting time go forward 1 hour and then another hour. And you watch where those raindrops go, they'll slowly come together and they'll all kind of cluster in the Mississippi and they'll all kind of go down the Mississippi. Something is contracting the state space in a dynamical system to make that happen. And that contraction is called dissipation. And so there are no attractors unless you have dissipation. So attractors only exist in dissipative systems. Now, nonlinear and chaotic dynamics exist in non-dissipative systems. We don't call them attractors. We call them something else. And we'll get back to that, mostly language. Okay. So that's, this is the forward pointer to that. When you don't have friction, well, I should say dissipation, because dissipation is both positive and negative friction, and that can matter. If you have no dissipation, your system is what's called conservative or Hamiltonian, then it can be very, very chaotic. Well, chaotic is binary. You can't be very chaotic. It's kind of like, pregnancy, it's binary. So chaos can happen in systems where there's no friction, but there's no attractors. It's just not called an attractor, it's something else. We are going to ditch this idea until after spring break. We are going to work in the realm where we all live, where there is friction at real world human timescales. And then when you come back from spring break, hopefully we all come back from spring break into a physical classroom, we will throw out friction and see what happens. And that's actually kind of fun. Get all sorts of interesting applications in the solar system. But where we're going now, and for the next week and a half or so, is into the dynamics of maps. Now, what's going on here? We're all used to time flowing like the second hand of a very, very expensive analog watch. Time flows. And it could make sense to ask, what time is it? And have your answer have, technically, an infinite number of significant figures. It could be 1.739 seconds and so on and so forth. My watch, which I don't know where it is, I have a watch, not a physical watch, not a e-watch or whatever you call them. And it has a second hand, and that second hand moves once per second. So it doesn't make sense for me to be thinking about something that's a difference between 1.5 seconds and 1.6 seconds. All I have is measurements of time that are in some sense quantized. And that's what I mean by a discrete time representation. Time only makes sense at discrete points, maybe 1 second, 2 seconds, 3 seconds. Examples of things like this in the real world might be like, I don't know, a monthly economic indicator or old-fashioned film. Again, I'm dating myself, but there used to be celluloid film that they put in cameras and it came out, and every 24th of a second, it had a representation of what's going on. That's a discrete time sampling of a continuous time dynamical systems. But if all you had was the film, that's what you would have. Similarly, if you're at a dance club and you're moving, and then they turn on a strobe light, and all you see is people doing this, that's what dynamics looks like in discrete time. Why all this ranting? Because there are a number of cases where discrete time dynamical systems are completely appropriate to think about, and thinking about them is mathematically way easier than thinking about the kinds of ODEs and pendulums and things like that we started with on Tuesday. And moreover, not only are there dynamical systems that live in that kind of space that are real and useful to think about, they also demonstrate a lot of the important concepts and properties that come up in this course. And they're mathematically way, way, way easier. So most courses like this, including mine, start by going through all the important concepts in the context of maps, discrete time dynamical systems, attractors, basins, yada, 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 all turn up in maps, but you don't need to deal with ODEs. Then I'm going to go back through all those concepts in the mathematically somewhat harder to deal with framework of continuous time. So we are suspending the notion of continuous time now, which is weird, but we're going to do it. And we're going to work with maps. And maps, the mathematics of a flow, going back to this, mathematics of a flow, you use differential equations to represent. The mathematics of maps involve difference equations, far less carnivorous. Every time I do this, let me hit the gray again. I'll fix this on Tuesday, my apologies. Anyway, a difference equation. So what is a difference equation? It is a box of mathematics, very much like what I drew before, except and it takes a state, it takes a state of the system at time n. This is time, the subscript is time. And it's going to be in integers. Remember, it's not allowed to be 1.37957. It can be 0, 1, 2, or whatever. And what a map spits out is something really nice. Okay, it tells you where the system's going to be next. It's not like an ODE. With an ODE, it looked the same, it took the same input, but the output was not where am I going to be next? It was which way am I going? And you had to do some more work to figure out where you were actually going to be. Okay, so very different. It tells you a difference equation, tells you, given a state of the system, what's the next state at the next time. Okay. So let's see. Mathematically, I mean, xn plus 1, you can write this down without boxes. I'm writing big enough. I'll try to write a little bigger so that you don't have to make the screen huge. So how do I get xn plus 1 from xn? I apply f to it. Very simple example of such a thing. How about the cosine map? So xn plus 1 equals cosine of xn. There's a map. It's what's called a 1D map because it operates on one number. So xn is not a vector. If you had a 2D map, you know, this could be a vector. So this could be a vector, but then that 1D wouldn't be right. So this is pretty easy to evaluate. You just use the cosine key on your calculator and you put in a number. And if you put in a number that's like kind of pi over 4-ish, and you hit the cosine key 3 times, so this is hitting the cosine key, poink, 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 poink. I got 0.9987 something or other. And then if I kept hitting the cosine key, it stayed that way. So after 3 times, that is after I got from xn to xn plus 3, I got to a particular number, and then every time I hit the cosine key after that, I got the same number back. So that's interesting. So this is a point in the system state space. This system, by the way, has a really boring state space that's just the unit line, right? It just has, this is the state space of the system. And what I've gotten to is, here was x1, here was x2, here was x3, and here was x4, and here was x. So this was x4, this is also x5, and this is also x6. So you see what I'm doing is, here's where I started. I hit the cosine key, I got there, hit the cosine key, I got there, hit the cosine key, I got there. I hit the cosine key, and I got back there. I hit the cosine key, and I got back there. So this point right here is a point in the system state space where if the system gets there, it isn't going to move. This has a name, right? This is a fixed point. Is it stable? Well, we can test that. All we'd have to do is change this number and see if it came back. And in fact, it would be. So this is a stable fixed point or attracting fixed point. What this means is that this dynamical system has an attracting fixed point. Okay, attracting fixed point. The actual value that it converges to may depend on numerics, like the algorithm, the number of significant figures in your calculator. There are interesting things going on here, but the point is that this point here, this x, I'll call it x star, is equal to 0.9987, whatever it was, is equal to f of x star. Okay, where f is the cosine map. This was the definition of a fixed point. A point in the system, that is equal to the forward iteration of that system. So here I take a point, I ask where it's going to be next. If I get back exactly the place where I started, that's called a fixed point. In order to figure out stability, we would have to put a little bit of a delta here and see what, or sorry, not here, but we'd have to put a little bit of delta here and see what happens. We'll do that probably on Tuesday. So that is what a difference equation looks like. And this is a pretty antiseptic one. Next one I'm going to talk about is not so antiseptic. It is a simple population model called the logistic map. And here's what it looks like. It looks like xn plus 1 equals r times xn times 1 minus xn. It's a quadratic. And xn here, there's a single number that is the state. So x is the state. N and n plus 1 are time. And this state is something like the ratio of the number of foxes in my backyard to the number of rabbits in my backyard, something like that. And R, which is a parameter, is something like the ratio of how many babies a rabbit has versus how many rabbits a fox eats per year, or something like that. I'm waving my hands wildly because I don't know the exact details, but this is a simple population model. And there are much more complicated ones that are better, but this one is actually not too bad. But our point in playing with it is to be able to play with it, not its relation to the physical world. So simple population model, sharks and fish, rabbits and foxes, R is hunger to birth rate or something like that. And to some extent, it makes sense that a model of population would live in discrete time because births and deaths happen at discrete times, not over continuous times. So, you can wave your hands about that. And again, difference equations like this have attractors, they have sensitive dependence, they have trajectories, they have orbits, they have limit cycles, all that kind of stuff. And that's where we're going right now. One big difference here is you do not need 3 dimensions for chaos in maps. Okay, you do not need 3 dimensions for chaos in maps. And there's reasons for that I can talk about offline, and we'll come back to it later as well. But you don't need 3 dimensions for chaos in maps. All you need is 1. And that's good because the logistic map, here's my logistic map, you need one number, X, one number. Okay, to describe the state of the system. This is a one-dimensional, nonlinear map. What makes this nonlinear? Well, there's if you actually write this out, it's R xn minus R xn squared. There's the nonlinearity right there. So this is a nonlinear map. It's a parabola. So it is a nonlinear map and it is chaotic. It lives, by the way, it lives on the unit interval. All of the values of X live on the unit interval 0 to 1. So if you like notation, you can say the logistic map is a map that maps the unit interval. I think this is a closed interval. I can't remember. I might be messing up square brackets versus curly brackets, but it's a basically, you can think of the logistic map as an operator that takes this unit line segment and stretches it vertically and folds it, stretches it vertically and folds it, just like people that make dough need bread. They knead the bread and then they fold it. They knead the bread and then they fold it. The logistic map does that to that poor little line segment, and that's how things happen. So let's try a few initial conditions. Let's say we have an initial condition of, I don't know, 0.2, and I need to pick a value for R. And I've got in my notes 2. And the equation again up here, xn plus 1 equals Rxn times 1 minus xn. There it is for your reference. So the way we figure out x1 is we just plug in 0.2. Oops, I got these backwards, but the idea, I hope. So that's, I put the xn here and the r there, but it doesn't matter. 1 minus 0.2. That's all. This is one line of code. This is part of why people start this way. And I did that out, I got 0.32. Then to get x2, you plug in. Okay, again, one line of code, 0.44. And I did this again, and I got 0.49. And I did it again, oops, 4, and I got 0.5. And I did it again, and I got 0.5. And I did it again, and I got 0.5. What's going on here? This is a fixed point, okay? Because there's one click of the map, click, 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 3 clicks, wink, 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 and then it stayed. So what that means is that 1 second it moved from 0.2 to 0.42. Another second it moved from 0.3 to 0.44. Another second it moved from 0.49 to here, there, and then one more second it moved to 0.5, and then it settled down. So if I plot this behavior, and now I'm plotting n, by the way, not t, and it's only allowed to take on integer values. Here's my 0.2, 0.32, 0.44, 0.49, 0.5, 0.5, 0.5, 0.5. Okay, so that's what the dynamics look like in the time domain. Now, remember, time makes no sense in here. We don't know what time is. We should not ever, 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 ever connect those dots because we don't know. It could be doing all sorts of wild stuff in there. Those foxes and rabbits could be doing all sorts of stuff between when the biologists came to ask how many there were. Do not ever connect the dots when you're making a plot in a discrete time dynamical system, because time does not exist between 0 and 1 and between 1 and 2 and so on and so forth. Okay, so this is a fixed point. It's a stable fixed point. It's an attractor. And these are, here's the initial condition, and this is the orbit, or we also sometimes call trajectory an orbit. This is the orbit or trajectory going to that fixed point. Okay. Here's something cool. We figured this out by plugging stuff into math. Okay, we could also do this graphically, and there's a really cool graphical solution technique that is not only useful, it's not really useful for calculating the details of the points, but it's very useful for understanding. And it is a plot of xn plus 1 versus xn. I mentioned this before, I think. We have a lot of representations that we use in my field, and we switch back and forth between them, often without narrating why. When I want to know something about the details of the time domain, I will plot with respect to time. But if I want to know something about the relationship between successive iterates, I might plot like this. Write down the map again. Okay. So I'm going to draw some things on this plot. First of all, I'm going to draw that. And that happens to be an upside down parabola that goes from 0 to 1. This is 1 right here. Okay. And if I make R taller, this is what happens. Sorry, not taller. If I make R bigger, the parabola gets taller. So this is what, yikes, escaping pencils, no escaping pencils. This is what happens as you increase R. There's an important landmark on this plot. Here's another important landmark. That equals sign. That's the unit diagonal. I hope you see why I'm not using PowerPoint. I mean, isn't this, this would be very, very different if I showed you the finished product, if I just showed you that on PowerPoint. And if I did that obnoxious thing of successive layers of the PowerPoint, that's just ugly. Anyway, this is the line where it is this, the following is true. Okay. Two very important places. Now, there's some important points here. On these points, this is true and that's true. So at these points, these little points, both this is true and that's true. So those are fixed points of the map. So those are fixed points of the logistic map. I'll just call it L. That's the logistic map. All this is L. So those are fixed points of L. This plot has some interesting names that I'll come back to, but let me first show you how it's useful. And what I'm going to do there is zoom in a little bit and explain. How do I have that there? I guess I'll use this picture. Okay. I'm going to redraw. I think I have this in orange, this in blue. All right. And now I'm going to do something funky. The act of plugging a value X into this right-hand side is equivalent to taking some value here, that's some value X, and walking up to the curve. Okay, so this is the act of evaluating the map L for that X, 0. Okay, so that's the first piece. Then the next piece is, well, okay, so that tells me, if I walk over to this curve, that tells me what X1 is. This is X0, that tells me what X1 is. So really what I want to do is I want to take this and I want to rotate it down and plug it in here. So this is going to be hard to draw, but I could imagine taking this length right here and rotating it down like so. Okay, and I would end up kind of over here someplace. Equivalent to that, because this is the unit diagonal. And this requires a little bit of thought. Okay, so I would ask you to think about this a bit. This act of taking this point, this length here and rotating it down to here is exactly the same as going from this point whap over to the main diagonal. And you can't quite see that because I haven't drawn it quite right, but this point here is because this and this are the same length. That's the same thing as me rotating that down. All right, so the act going up like that is the act of evaluating L. And this right here is the act of kind of setting the result or plugging, how do I say this? Setting the result equal to xn plus 1 kind of. All right. Now what I do is I keep going. I go up to the curve and I go over and I go down, and I'll make this bigger later on, but you get the idea. So you see what's going on? If I blew that up, it would be going, No, that's the wrong way. I did it the other way. It goes up and then over. That's what's going on here in my magnified view. If I looked at that in the time domain, covered with blue ink, what I'd be seeing is some initial condition, and then it goes here and here and here and here and here and here. Okay, xn. And again, do not do this, but you see what's going. It's going bup, 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 bup. So it's kind of like when you push on your car's bumper and you don't have good shocks and your car goes wonga, 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 and then it settles. So it's a damped oscillatory convergence to a fixed point right there. Now, if you look closely at my drawing here, you can see why these things are called cobweb diagrams, okay? Because they can end up looking like cobwebs. They're also sometimes called, hang on, let me get to the proper camera. They're also sometimes called correlation plots because, as I said, they bring out the correlations between xn and xn plus 1. They're also sometimes called return maps because they say, okay, well, there's xn, how does it return? Well, its return is xn plus 1. So lots of different names, but this is the idea. So let's draw a few more. Did that one. Do a few more. Here's, oops, switch. Here's the return map. X, it's the first return map. There's that main diagonal. There's the logistic map curve. And let's see what I'm going to try actually to use a pencil for this so I don't get blue ink all over everywhere. Let's start kind of here. And so here's my x0. And I go up to the curve. There, hitting it, actually it's better with a pen. Hit it there. And then I go over to the line, down to the curve, over to the line. So you see what's happening? Let's see, over to the line. Okay. So this is quite different from that. Quite different. One is going in, the other is going out. And indeed, if we looked at this in the time domain, we would see something like this. Right? So that's a growing oscillation. So think about it for a second and look at these two and consider what is it about the geometry that made this one go in and that one go out? And I have a picture to help you think about this. What is the critical feature there that made the trajectory diverge from the fixed point? Any ideas? Feel free to sing out. I know I haven't been using a lot of class participation with Zoom, but we'll get into it. Any ideas? What is the critical feature about the blue or the orange that's making this happen?
The parameter R.
The parameter R, definitely. You see that I've drawn a taller parameter here. So what is it about locally right here that's different? Any ideas? I see a chat. Maybe I'll actually.
If it intersects under or above the curve.
It's definitely something about the intersection. Let me make a suggestion, and I think I'll find a different piece of paper. Imagine if you've got this parabola and you've got this line, and you don't just try one point here, but you try like a band of points. Okay, so you see that this band of points got thinner once it bounced off the curve. And that's going to make things contract. It's actually what it is the slope at this fixed point. Slope at the fixed point. Because if this slope is, if the magnitude of this slope is bigger than 1, then that ribbon of points will get thicker every time it bounces around, as opposed to thinner. So the critical feature there that made the trajectory diverge from the fixed point is the slope of the blue curve, the logistic map at the fixed point. Okay, good. And yeah, somebody pointed out that that's the effects of R, because if you look at, again, this plot, I'm going to stop drawing the axes because I'm getting too much ink on me. There's the line. Here's R for low. Here's R for bigger. Here's R for bigger. Here's R for bigger. And if you look at what's going on here and here and here and here, you can see the slope of the blue curve as it intersects the orange line is changing. And if that's low, like here, we can do an experiment. And this is what's really cool about this representation, is you can just do these experiments and see what happens. Whereas when it's tall, see, you can just tell from the geometry, just with a paper and pencil, which is really pretty cool. Okay, good. All right, so remember the pendulum that could go, the pendulum that could do something like this, or it could do something like this, where this was a 1 cycle and this was a 2 cycle. Well, changing R can actually make the logistic map go into a 2 cycle. And it's a little bit hard to draw. So give me a minute. And in the time domain, it's easy to draw. And this actually happens in population biology, because one year there'll be lots of foxes and not many rabbits, and next year all the foxes will starve and the rabbits will have babies, and then there'll be lots of foxes, lots of rabbits, lots of foxes, lots of rabbits. So this happens. How do we reverse engineer how that comes out on the return map? That's actually a little bit of a challenge, and I need to cheat by drawing the 2 cycle first, and then draw the rest of the, this would be not as useful at all if I were doing it. There we go. There's the logistic map. This is L. And this is the unit diagonal. And if you start at this x0, walk up to the curve, you walk over to the line, you walk down to the curve, you walk over to the line, and you see what happens. You end up in a square. And what you would see is this value and then this value. And then this value and this value. This value and this value. So here, this is this, and this one is this. So maybe I'll do something. So this is the green ones. That's this. And I don't have any more colors out. So this one here is these guys. Okay. Hard to draw, but this is the asymptotic behavior of the system for a wide range of R values, which is really pretty cool. And you'll see this in your problem set. And your problem set is going to be literally a line of code to do the calculation and whatever you need to do the graphics. So that's problem set 1. We'll get back to that a little bit more in a sec. Now, we can actually describe this kind of thing mathematically by simply taking a new map and writing down what happens in 2 clicks of time. So xn plus 1 is equal to rxn times 1 minus xn. Well, xn plus 2 is r times xn plus 1 times 1 minus xn plus 1. We can substitute in, we can take this whole mess and put it in here and put it in here, and we can get a map that is a box of mathematics that is the logistic map composed with itself that takes in xn and spits out xn plus 2. So our original box of mathematics, which was just L, the logistic map, takes xn and spits out xn plus 1. This is the what happens in one time click. Oops, there we go. This is the what happens in 2 time clicks, and no fair looking in the middle. This map doesn't tell you what happens for xn plus 1. It just tells you about xn plus 2. So this is the, again, this is the 2 time click map. And the way we can draw a picture of it. And what it does is it tells you, given an xn, what happens to xn, oops, 2. 2, 2, 2. And this thing looks kind of like a 2-humped camel, like so. And you can do all of the same reasoning about starting here and walking up to the curve and yada, yada, except the dots that you're seeing here are every other x. So this is x1. This would be x3. This would be x4, 5, and so on and so forth. So this is, again, every other click. And what is this thing? What is this thing? That is a fixed point of something. It's a fixed point of the map L composed with itself, which is the 2 time click map. So it's a fixed point of that, which means it's a 2 cycle of L. Okay, it's a 2 cycle of L. All right, and your task in problem set 1 is to write some sort of class or procedure or function or something or other. Maybe it's called logistic. And it takes 3 inputs, an initial condition, an R value, and maybe a number M. You'll learn that I am a Lisp and Scheme programmer, so you'll see that by the placement of my parentheses. And what this thing does is it basically takes, it evaluates the logistic map M times, click, 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 using the value R from the initial condition x0. So it should iterate R xn, 1 minus xn, M times from x0. I should say iterate. And then plot it. And I want you to plot it 3 different ways. I want you to plot it in the time domain. I'd like you to also generate plots in the first return space and in the second return space. Okay. And then I want you to play with R and play with X0 and look for bifurcations and other interesting stuff. Okay. And you can do another procedure, by the way, that adds a second number there. So it might add another number right here of, I don't know, N, where it iterates the logistic map M times from X0, but it throws out the first N iterates or something like that. So you might use that, for example, instead of, if you wanted to look at the transient behavior, doing some sort of weird transient stuff, and you just wanted to look at the asymptotic behavior, you would use this N to discard the transient. That might be useful as well. Okay. Let me switch here and switch to this. Okay. Again, I don't want you to connect the dots on these plots. And I will grade this problem set myself. The grader won't grade it. So I will be able to help you calibrate. That's part of why I do this. And when this is not the kind of course where I say you must find X, Y, and Z. I say play with R, play with X0, and look for interesting stuff. Where I mean interesting means from the standpoint of this course. And I want you to use the language of this course. I don't want you to say, oh, it looks like it kind of gets to 0 and stays there. You have a word for that. Use your words. Fixed point. Okay. And there's some more guidance on the problem set handout, and I'll hang up for a bit if people have questions, and otherwise have a great weekend, and I'll talk to you soon. More chat, let's see. Oh, yes, you can use Python. You can use anything you want, any code you want. You can use Excel if you want, it won't work.
Professor, I have a question about the book.
Sure.
So are there any like special resources that like we need with it, or is it cool if we just have like a physical copy of it?
Fine if you have a physical copy. Or
All
the
right.
digital. I don't even know. I don't even know what the digital copy comes with. I have no idea. But yes,
Okay, we just need the book
the
itself.
book.
Okay,
And
and
once-
also is the MOOC free?
Yes.
Okay, great.
And I have a couple copies of the books if anybody's doesn't want to buy one. I can load them out.
Do you have any office hours before Tuesday?
My office hour, no, actually, oh, right, because it's Martin Luther King Day. I will be around on Martin Luther King Day, so just email me, we can set something up. But normally, Ella has office hours on Mondays, but I forgot that this is the holiday, so that's a problem. So email me.
Okay.
Iris, that's Iris, yeah, email me and we'll set something up.
Okay, cool. Thank you.
Yep.
Yeah, I got 2 questions about the textbook and the MOOC. So I see there's like an email. So first of all, yeah, there's like an email like 4 days ago. Something about opt-in for the textbook, and then if we opt in, it's on the Canvas. So
Yeah.
I don't see it on Canvas though. know-
This is the first time I've done this, and I only know
Okay.
what the bookstore has told me. I will go back and look at the message that they sent me. If you email me,
Sure.
so I remember, I'll forward you that message, and I think it said exactly where you find them.
Yeah, I think I need that email too, because I signed up maybe, Friday or Saturday. I was changing courses a little bit. So I think I missed your January 5th email. That was like an introduction. So I
Oh.
also don't like know what the MOOC is, or like where the link is, or
Yep.
anything
So the
like that.
MOOC,
So I should
the
email
MOOC-
you.
Yep. If you look at the syllabus on the course webpage, not the Canvas page, the Canvas page points to another webpage, which is the full-on webpage for this course. That there's a syllabus at the top of that page. It talks all about this stuff. It's a 6-page long thing.
Okay. Yeah, I was trying to find like the course website, but
That's posted on the Canvas page.
do you know like what sub tab?
It's
Maybe
it's under an announcement.
okay.
Yep.
Is it all right if I just email you, and can you like forward me the link for that, and I'll just bookmark it because I'm not seeing it for whatever reason.
Okay, so somebody just put it in the chat. Thank you. Thank
Oh,
you,
okay.
Jason.
Okay, that works too. I'll just do that. Yeah, just do that.
Yep.
Okay, that should work.
All right.
Thank you.
Yep. But do email me so I send you the how to find it.
I'm leaning toward getting a physical copy, so I'm just wondering what editions, because I don't see that on the syllabus.
Doesn't matter. Anyone's fine.
Okay.
And when
So-
I have reading assignments, I don't put pages, I put section numbers for that reason.
Okay, awesome. Thank you very much.
Yep. Do you have a question, Neil? Okay, then I will. close-
Yeah, I
Yeah,
put it
go
in the
ahead.
chat. The problem set is due on Tuesday, right?
Correct.
Okay. And is there like a time that it's due?
No, I'm not going to grade it till Wednesday. I mean, don't let it expand to fill all available space, but this is a course for grownups and I'm not really nasty about, I'll take off 2 points if it's half a minute late. So just get it in sometime Tuesday.
Okay. Can we
Okay.
turn those in on Canvas?
They're on, submit them on Canvas.
Okay,
But
thank
the
you.
the document itself is on my webpage.
Yeah, I found it.
Okay,